Welcome folks. In today's video we're going to learn about the concept of power, and this is a word that we hear all the time and it's thrown around all the time, but in today's video we're going to look at it from a physics standpoint. We're going to look at how it relates to the needs of our planet, and we're also going to maybe investigate how powerful we truly are, and whether we're as powerful as a horse. Now, power is defined as the rate at which work is done, and we know that in order for work to be done, there has to be a change in energy. And so sometimes power is defined as that change in energy over change in time. It's how much energy has changed over a time period. Now, if we look at this scenario here, it used to be measured in an old measurement for power was not watts before the SI units came along. Instead, it was measured in terms of how powerful a horse is. Now, who actually came up with this original measurement of power? I don't know. Maybe it was James Watt, the scientist that Watt is named after. However, one horsepower is defined as 736 watts, or 735.5. And what that essentially is it is the amount of energy that a horse is capable of doing, a standard horse, I guess. And this is measured by looking at that change in energy. So if we come back to this scenario here, and we say that it's lifting this crate, and 1 horsepower, therefore, remember, would be the change in energy. This time it would be potential energy over time. And 1 horsepower is defined, 1 HP is defined as lifting a 75 kilogram box 1 meter multiplied by that acceleration due to gravity, which we'll just write in as 10 meters per second squared multiplied by 1 all over 1 second. So if you can lift a 75 kilogram weight 1 meter in height or in a 1 second time period, then you are indeed as strong as a horse. Or maybe I should say as powerful as a horse. And another way to measure this would be to look at this scenario here, where we have a person maybe jogging up a stairs. And when we're looking at this, the amount of power developed would be how that energy can change from, let's say, point A to point B. And we're just going to draw this in. So point A might be here and point B might be here. So if a person can run up to point B, then they've increased their potential energy. There definitely would be an increase in potential energy there. The potential energy has increased because mg delta H relative to the bottom has increased, the height has increased. So if you can figure out how long it would take the person to do that, you can get a feel for how much power they have. So again, you would just get that mg delta H and divide it by the number of seconds to figure out how powerful that person was. Now, we could also have a different person over here. They're, more powerful evil twin, let's say. And they could decide, you know what, I'm not going to go up that way, I'm going to go this way. And it's faster. Well, in that case, the same height, we would be dealing with the same height, but in a shorter time. So it is, if we accepted that this height value is going to be the same, so this delta H, and remember delta H is always vertical. So if that delta H value is the same, but for the second person, its time goes down, they can do it in a quicker time, then this person on the left would essentially be more powerful. Even though the change in energy has been done, it's been done in a faster time. So let's look at some practice problems here. How long will it take a motor with a 0.5 kilowatt power rating to do 1,500 joules of work? Well, we just got to make sure that we understand our equation for power here. And I've just written it in here. Power is delta E over delta T, or delta W over delta T. where there's a relationship between work and energy. And so we can isolate for what we need here, which is time. So we're just going to do that. So we're going to write it out, and we're going to say that it has that much work. So 1,500 joules of work all over time. And of course we can put in our our figure for power here, because we were already given that figure, and we're going to write it in terms of watts, so it would be 500 watts. And then we're going to isolate for time. So time is going to be 1,500 joules. And we're going to spin out what a watt is. A watt, remember, is joules per second. So we're just going to write it as that. And the reason why we're going to write it as that is just so that you folks can all see that these joules will cancel, and you're going to end up with seconds. Okay, so we're going to end up with a figure in seconds, which is going to be 3 seconds. So it would take a motor, and this is a power reading on the motor. Normally motors will have these power readings, and it is, in a sense, it's their ability to do work, and it's a measure of how quickly they can do that work. Another quick example is below. How much power is developed by a 6.1, 6 by 10 to the 1 kilogram girl as she runs up the stairs 4 meters in height in 3.5 seconds? Well, let's have a look at this. So P is equal to delta E over delta T. We know that the delta E was caused by a change in height. It could also be a change in kinetic energy, which would be half mv squared or delta V squared. We're just going to plug in some of those numbers, and we are going to get a figure which is 2,354.4. 354.4. This is a measure of delta E, so it should really be in joules. And now we're going to go and put that over here, 2,354.4. We'll leave in those extra significant digits for now. And then when we use our calculator on that, we're going to get 672. Okay, so 672 watts. And we're not going to worry about significant digits, even though that is important. You might want to trim that down just to one significant digit, because that's the least significant in the question. Okay, so 672 watts was done by the girl. Not quite 1 horsepower, so not quite as strong as a horse, or as powerful as a horse, it seems. Well, we can't talk about efficiency in machines without looking at how or the power of machines without talking about how efficient they are. And that efficiency has consequences for the earth, because we want things to be as efficient as they can, so that we don't see energy wastage and all that energy being removed as friction and heat and so on. So efficiency is a measure of the ability of a machine to convert all of that energy in to energy out, and we write it as a percentage. So if you look at the diagram below, we've got our energy in, and the machine does what the machine does, and it has energy out. Now we should also at this point say that that doesn't look right, and the reason why it doesn't look right, maybe stop and think about this photo here to try to come to an understanding of why it doesn't look right. And the reason why it doesn't look right is because we cannot get more energy out than we get in. This would be a more realistic view. And the reason why the green arrow, the energy out, is less than the red arrow is because some of that energy is actually lost. And you can look at previous videos if you want to understand why. This is what is an open system. And so because of, friction and so on, there's energy loss. So what do we take from that? The efficiency can never be more than 100%. And some efficiencies are actually really, really low, 5, 10, 15%. So efficiency is a measure of energy out over energy in multiplied by 100. So where is that relevant in our lives? Well, we can see this laid bare if we look at even just the evolution of light bulbs over the past number of years. And if we look at that, we'll see that we had the good old incandescent light bulb, and if we see that in order to produce a certain amount of lumens of light, 1100 lumens of light, which is a measure of the light given off, we needed to use 75 watts. Now, if we compare that with the compact fluorescent, or indeed the LED light only needs 11 watts. So it's using so much less energy. And the reason why it's using less energy is because the incandescent light bulb was really more of a heater than a light bulb. And most of that heat, about 95% of the energy given off by an incandescent, was actually in the form of heat. We can have a look at this again. If we look at the evolution of light bulbs, I'm just going to leave that on the top of the screen so you can see it, and we're going to look at a problem. So our problem is at the top of the screen here. I'll let you read out that problem. So we have a light bulb efficiency of only 2%, determine the amount of power actually turned into light. So very important here that we frame this out. We write our relevant equations, we look at our givens and so on. So first thing is we're going to write efficiency in terms of energy out, energy in. You will also see that it is the same as P out over P in multiplied by 100. Now the reason for that is because P out is equal to, remember, is equal to E out over time. And P in is equal to E in over time, and those times will cancel. So essentially, because time is going to be the same in both instances, we can rewrite as P out over P in. So we write that as 2 is equal to P out over E in. We bring our 100 across here, and we rewrite as 0.02. And then we just need to isolate for P out. And when we do that, we're going to get 60, whoa, pen's not behaving itself here, multiplied by 0.2, which gives us 1.2. So 1.2 watts is the actual power that was generated by this bulb. We're just going to look at a more complicated question, slightly more complicated here. Conveyor roller system transfers crates from above to a loading dock 1.6 meters below. The roller is going to do what rollers do best and just keep chugging along, and this box is going to end up down here. We have certain things. If the 45 kilogram crates are placed at the top, what speed will they have at the bottom? So if they're placed at the top part here, what speed will they hit the bottom at? Okay, so and we also know that the conveyor isn't 100% efficient. That's real world because there's some of that conveyor energy, that energy in being lost as heat and friction, and we'll hear the rollers rolling. So a couple of things that we need to make sure that we understand here is that we have a scenario where ME1 is not equal to ME2. These are the mechanical energies at the beginning and end. So we would have to rewrite this that ME2 is only equal to 0.85 of ME1. Where do we get that from? Well, we said that it was 85% efficient. So it's only 85% of the energy at point 1 is what we're seeing and what we get at point 2. And the rest of it gets gets lost to the surroundings. So we can do a little bit of didgery-pokery here, and we can get rid of the m's because they're on both sides. We can multiply the 2 here. We can bring it across and multiply it. So what we're going to get here is 1.7 multiplied by G times H is equal to V2 squared. So now we need to just multiply those values together, and we're going to get 26.7 is equal to V2 squared. And if we take our 26.7 and we square root it, we are going to get approximately 5.1. So I'm just going to write it down here. 5.16. 5.16. Oh, what's happening with my pen? Dear God. Okay, so meters per second. So what's important here? We needed our understanding of conservation of energy. We needed our understanding of what efficiency means. And when we do that, we can get to a point where we're looking at what the speeds are. And this is very important for machinery and anything which involves conservation of energy and not wasting energy. So hopefully this video was useful. If you liked the video and it helped your understanding of this, give us a wee thumbs up, please. Thanks.